Okay, now we'll add moisture into the mix. You thought atmosphere was complex before, wait till you get this one. Moisture adds tremendously to what happens within the atmosphere. So, with that, let's take a look at this a minute. So here you have water vapor. Where does water vapor come from in the air? Oceans, puddles, rivers? So evaporation of a liquid causes water vapor. Well, all right, water vapor is a gas, so the molecules are moving further apart. So in order to become a gas, some of the heating had to go into that water to make it a gas. Just like when you boil water and you see the steam coming up, some heating had to be added. So in order to get water vapor, heat had to transfer into that water. So with that, think about it, the sun's shining brightly. Water vapor is getting pulled up into the sky because some of that energy from the sun is being used to heat the water and cause it to evaporate. So let's take this if you had a whole bunch of rainy days and there's a lot of water, the ground's saturated, there's lots of puddles all around, but now you have a bright sunshiny day. What happens is some of that sun's energy goes into heating that water, evaporating it, a cooling process. So you wind up with water vapor developing, but the temperature that day does not get as warm as it normally would. Now, if you go from water vapor, and say we lift it up in the sky in an air parcel, what happens? That parcel gets colder. The water vapor is going to eventually get to the point where it needs to condense. It's going to cool so much, and it's going to go back into a state of water. When it does, heat is released. That's why when I talked to you in the last thing about moist adiabatic lapse rates, they occur because that heat has been released as the water is condensing. Oh yeah, and keep going here into an ice state. Again, a solid. So heat has to be released as well there. So more heat is entering the atmosphere when a liquid changes into ice. So now the opposite direction, if ice in the atmosphere melts as it's coming down through it, say you had snow up at the high top of the atmosphere coming into an area that's warmer, as it's melting, well, guess what? It had to be taken in heat to melt. So it actually is trying to cool the atmosphere there. And sometimes you can get things from downbursts and thunderstorms and stuff where that kind of thing really shows up. But otherwise than that, it actually can cause a little layer of warmer air, and sometimes that can change snow to rain, or if it's not as much as you think it's going to be, maybe it stays snow coming down and it doesn't do it. But it's all these interactions here that you need to have at least somewhat of an understanding of. So vapor pressure is just one measure. There's lots of measures of moisture. It's just one. And at every different temperature, something called saturation vapor pressure, which is when the air parcel can know no more water, changes. The warmer the air, the bigger the saturation vapor pressure is required. You need more water. So in other words, in the tropics, you guys can hold lots of moisture. However, if you're at the North Pole, you can't hold a whole lot. And they are just things. One of the interesting things is, and you're going to see why here later, over ice, the saturation vapor pressure becomes different the colder the air is. And that actually influences a lot on precipitation. Relative humidity is just a percent of how close the vapor pressure is to saturation vapor pressure. So if it's 100%, then the air is saturated. If the air is 90%, it's close. If you're like in California right now, where the relative humidity is about 5%, it's pretty doggone dry. There's not a lot of moisture in that parcel. It can take a whole lot of moisture to make it saturated. Another measure of moisture is dew point. That is what's plotted on all weather maps. Dew point is just a measure of moisture. The closer the dew point is to the temperature, the more saturated the air is. So if I'm looking at a surface weather map right now, and I wanted to see where the air is most saturated at, I'm looking for that spread. So let's bring that up real fast here, because I meant to bring it up before. And we'll show you what's going on that way. So it is a surface weather map coming up here. There we go. And we take a look here in this drier air out here, 52, 39, pretty good spread. Look out here in California though, 49, 12. So yeah, it's moist over the water, but inland, and that temperature is going up today. This was done in the early morning out in California. Oh, down here in Florida, look at it. Dew points are in the mid to upper 70s. There's a tropical system trying to develop down here around Key West. And you can see they're fairly close to being saturated, but they're also very, very high. So that's just an example of what the dew point can show you on the weather map. If you're looking for fog in the morning, look at the dew point to see how close it is. When you're reading a METAR, dew point's right after the temperature. So if you're close to each other values, you know your air is getting pretty close to saturated. All right, how clouds form. Clouds are just water vapor that's condensed. Well, guess what? Water vapor can't condense without a condensation nuclei. Things such as salt, dust. They're microscopic particles in the atmosphere that allow condensation to occur. So that is what a condensation nuclei is. If you have that, water can start condensing when it reaches saturation. If you don't have it, water would actually cool and continue to be about 300% relative humidity before it actually condensed. So you can see these things are really important. Oh, one other thing. If you're down in the tropics, for example, like several of you are, and you've got the ocean around you, guess what? Salt is really great as a condensation nuclei, and that's probably what most of yours are. However, if you're in the Midwest or in West Virginia, a lot of it is dust. So that starts the cloud process and forms it. Ground fog forms. We talked about cold air being denser than warm air. Think about where it's going. I don't know if any of you are familiar with Charleston's airport in West Virginia, but if you ever fly into it, you're landing on top of a mountain. In the valley is the Elk River and the Kanawha River around it. The air cools on that ridge, and I used to work in Charleston. And when it cools, what's it do? It's heavier than the air down in the valleys, so it's sinking down. So as the night progresses, the air cools more and more, and eventually saturation occurs in the coolest air, which is down, believe it or not, by the valleys. In this case, it even has a river there to help bring some moisture into it. So that's why a lot of times you can actually see the fog kind of percolate up out of the valleys, growing upwards with time as the air starts saturating down by the river, and then you're building higher and higher till it reaches the airport and maybe closes it from fog. The same would probably hold in Beckley in some places. So I just happen to be more familiar with Charleston. And advection fog, okay, mountains also cause it. Think about the air rising. We talked about it, and I showed you an image earlier. Upslope fog would be another reason to fog. One I have, you think about, say fog formed over the Gulf, over the Atlantic Ocean. and was moving westward. That area of fog is advecting. We've talked about advection, the temperature, moisture, and all kinds of things in the weather. And it can keep on moving and come inland. I was at a football game, high school football game in Tallahassee when I was in college, and there was a very strong southerly wind that day. And that evening, you could actually see fog begin to come in. And if you looked at the satellite and the observations, there was dense fog out over the Gulf of Mexico. And as the game progressed, visibility kept getting worse and worse. So fog can actually move inland from the waters. We've talked about latent heat and condensation and all of that. Clouds, one of the things I wanted to make sure you understood is cloud amount. So clouds are measured in each layer of height. So if you have a very small little bit of a cloud, it's a few. 4/8 of a cloud is scattered. 5/8. Oh yeah, one of the interesting things is they build up. So for example, this might only be 3/8 of the sky, but there's another 5/8, 4/8 covered here, and one that was not seen before. So now you wind up with a broken. And when you look at the total, add another one, another broken. So your ceiling actually is the lower of the brokens. So remembering this is not your ceiling, but this is. However, if this layer of clouds grows a little bit, it might become your ceiling. So this is just how clouds are measured and put onto a METAR. And visibility is done exactly the same way, except it's how far you can see into fog or into the air. So if part of your, and dividing it again around the airport, if half or more of the airport has one visibility, that's going to be the reported visibility. However, and it's going to be whatever the lowest is for half of it. However, if you keep going out, you're going to get, you could wind up like in Charleston, for example, when the fog comes up at the end of the runway, it's only a part of it obscured and down in visibility. The rest of it might be 10 miles. However, if the fog keeps building and coming over more and more quadrants, all of a sudden you might go from 10 to a quarter, even though you haven't really covered the whole runway. And obscurations, and ceilings are all measured into a cloud. So let's take a look at some of this, just looking at a sounding and looking how moisture impacts it. I wanted to have you a means of looking at how much moisture can actually occur in the water. Precipitable water is basically a measure of if you dumped out every ounce of moisture in this layer here, which is over Tampa, you would have 1.93 inches of rain fall out. And that is a lot of moisture, and it's only going to happen, you'll notice it's a very warm day down here. Dew point is on the left-hand side, temperature is on the right. Look how close they are here. A little further apart, but they're still fairly close all the way up. So there's a lot of moisture throughout the whole atmosphere here. And if you're looking at this in the sound clouds here, with precip forms. Now, we know there was some showers and thunderstorms in here, and we saw the convection and the stability going on there. All right, as the air rises, it cools, and eventually it's going to reach freezing. But guess what? Without ice condensation nuclei, here we go again with more nuclei, and they can be salt, something similar to that, or some types of dust. The air will not freeze until it gets down to minus 39 degrees. But because of it getting these particles in there, it can start freezing at about -8. And guess what? That also corresponds. You can't have lightning without at least having some ice in the cloud. So that means if you ever see lightning occurring in the cloud, the air temperature must be below -8 degrees. So if you knew where -8 degrees in the sounding that day, you would actually know how high that cloud would be, at least. So you can see lots of moisture coming in and these clouds bubbling up. I wanted to look at these clouds in water vapor. Water vapor images, there's 3 of them we have access to now. So we'll start off at low water vapor. This is looking at water vapor between like 5 and 1,000 feet. So it's pretty low in the atmosphere. And you can kind of see it. Here's the tropical system. Here's that. So let's go back to it here. And if we go to next level up, mid is like 10 to 15,000. And again, lots of moisture down with this tropical thing here. And notice how they're kind of coming up out of the tropics into it. However, there's a lot of dry air right in this part, just to the west of it. So if I'm looking for something to develop, for example, from this system here coming in, it's going to have a lot of trouble. It's going to be dealing with a lot of dry air there. But notice the dry air here as well. And one of the questions I want to ask you about, think about the tropopause. Tropopause is basically the change from the stratosphere to the troposphere. Stratosphere is extremely, extremely dry. So if it mixes down some stratospheric air, if there's a very strong jet, the stratosphere might get kind of mixed in here sometimes. That's going to where drier air is going to tend to focus. And if you wanted to go up a little bit higher, we can really see it more in the upper, at the high levels of clouds. And you can actually see it pulling right in here, drier air in, kind of helping the jet stream. If you were looking for the jet stream, you would look for this kind of a pattern with it, because stratospheric air is getting pulled into it. So, I hope you got a little bit out of this. Let me know if you have any questions.